I will chair today the seminar by Elena Spagnuolo, who is a researcher at INGV, and she will present us some recent achievements and data on the frictional strength of sediments on samples taken in subduction zone. And so the rules, Elena, are always the same. You make your presentation. We have more or less 1 hour, and we would like to have some times for discussions and comments that I will be happy to share. So Elena, the floor is yours.
Okay, thank you very much. Thank you, and thanks for being here today. Massimo was introducing my title, recalling this very old discussion between Zoback and Scholz. So I take the chance to make an important distinction. So here I just want to investigate the concept of strong or weak of fault materials. That means trying to reason a little bit on the mechanical properties of these sediments, which are essentially fault gouges. Therefore, the outline of my talk is this, and I'd like to review previous literature on the mechanical properties of these sediments. So I will start with some motivation, and we'll try to recall the experimental methods we try to set up to investigate these problems. And in the end, I would like also to present some novel results on a particular case study, which is the case of the Sumatra Andaman fault region, subduction region. So why sediments? Because the sediments constitute the shallow section of subduction margins. So if you see this picture here, you can see also the thickness of these sediments in these margins. So the thickness can be very, very large, also greater than 4 kilometers. And subduction margins are relevant because host two of the largest geohazards, the megathrust earthquakes and tsunamis. And still we have a large number of key questions, which are in particular, what controls the up-dip extent of subduction zone, what is the real size of large earthquakes, what processes generate a spectrum of slip behaviors, what causes tsunami earthquakes, and so on and so forth. So that's why sediments are particularly relevant. And sediments are made of clays, essentially. So you can see here the map again with the thickness and the other information about the type of margins, and also the location of the subduction interface earthquakes, which are pretty large. But also this map is full of other information, like, for example, the location of slow slip events. So in time, this kind of map is becoming more and more informative of all the characteristics of these subduction margins. For example, we also retrieve and cored and logged these borehole, deep boreholes in these IOC programs. So we know also the type of materials. So these sediments are in fact made of clays. The component of clays is mainly smectite, illite, some components in chlorite and kaolinite. This is an example from Sumatra in Rosenberger et al. 2020. And you can see a similar composition also at the Ikuranshi. This is from Underwood 2020. And you can see that the total clay content is pretty large. And then you have components also in feldspar and calcite. This is the case from the Japan region. So here you can see again in different sites that these sediments are mainly made of clays, of pelagic clays, but also woods, so some with components of calcareous materials. So sediments are important. In fact, we have at least a couple of examples of recent models that try to incorporate the mechanical behavior of sediments in these models. One of the major achievements in the last years is the fact that the computational time now permit to introduce this kind of details. This is a work made by Shane Murphy in 2018. We collaborate providing the right friction laws. One of of the main difference of these models respect to other models is that we try to incorporate also friction laws specific for clays and friction laws specific for rocks. So this is essentially the configuration of the crust. This is the model that Shane was running, and one of the important results is that he was able to essentially model all the type of events which were recorded in this region, the same that hosted the Tohoku in 2011, simply by accounting for sediments. Another recent example is the one that Alice presented us a few weeks ago. One of the messages of this paper is that the tsunami genesis and earthquake dynamics are controlled by a long arc variability in regional tectonic stress together with depth-dependent variation in rigidity and yield strength. In this figure, there are the cases that they were investigated, and one thing that was important for me was the definition of stronger sediment versus weaker sediments, which is also one of the motivation of the title of this talk. So weak or strong. Before entering this kind of discussion, I would like to discuss a little bit previous literature about the definition of the mechanical properties, in particular of the sediments, and to show some experimental results. So this is a quite famous sketch of a subduction zone. This one became quite popular in the recent years, and a large number of authors are adding details and recent observations. These schematics essentially envise here a region of a stable, a seismic stable region made of these sediments. And this was from Ley and Bilek back in 2007. This sketch essentially incorporates two important concepts derived from the theory and practice of laboratory earthquake mechanics. And these observations were also validated with seismological, geodetical, and structural observations. So when we build this kind of sketch, we incorporate these two concepts, the frictional strength and the frictional stability. So the expected behavior before 2011 was this one, in fact. And the idea was that these clays, these sediments, the region made of sediment was a seismically stable. So meaning that it was creeping continuously and therefore act as a sort of permanent barrier to the propagation of earthquakes. Since seismic stress cannot build up in this particular seismic area, there is no stress to be released in the earthquake. Any seismic rupture traveling through such an area would stop dead in its tracks. And this is from AWAC 2010. After 2011, it became quite clear that it might not be the case, because during the Tohoku earthquake in 2011, we got this very large magnitude event with slip of up to 40 meters, even someone says also 50 meters of slip. So it's interesting how after 2011, this behavior was continuously revised and updated. For example, one of the last review that came into my mind is one of Baer and Borgman in 2020, where this region was populated with different ideas of they can host tsunami earthquake, shallow creep, slow slip events, and tremors. So what is happening here? How we can't justify this kind of behavior? Maybe it's worth starting again from the definition. And here we are. So the definition of weak and strong. The mechanical properties can be divided, in fact, in frictional strength and frictional stability. So when we say weak from a definition, that means lacking in force, and usually we refer to strength. And in earthquake mechanics, this is linked to the ability of all material to accumulate the stress, essentially. We can read in a nice paper by Collettini et al. 2019, some review about weak versus strong fault materials. Strong means strength consistent with column criterion under Bayerly friction, so friction should be in between 0.6 and 0.85 to be strong. Then there is a definition of weak fault, which should be like having friction less than 0.3. Then there is the concept of frictional stability. Unstable, by the definition, means having a strong tendency to change. In earthquake mechanics, it's generally quantified using a rate and state approach, and there is a very extensive literature about this. One of these is Scholz 1998, Maron 1998, where it appears that we have some critical parameters that determine if the fault is stable or unstable. So this is a recent paper, Ricari 2017. It was nice because the question was if sleep instability associated with earthquake nucleation depends on absolute fault strength. And the attempt here was to find a correlation and a relation between the coefficient of friction and the stability, so between strength and stability. And the answer again is they are independent, might be correlated, but are independent. Also, strength is variable. We have quite an extensive literature now saying that it can be strong, but it can become weak. For example, if we have fluids, fluid-rock interaction has the effect of reducing the strength. So this is an effect, for example, take chrysotile with water reduces the strength of the 70%. Then we have other examples saying that, for example, during the deformation, you might have the replacement of strong minerals with weak phases. This is an example from Zhang et al. In 2019, but we have plenty of other papers saying and suggesting the same. So the friction coefficient reduces as soon as you introduce phyllosilicates inside the sample. And another possible motivation is that, again, during deformation, you might have a structural organization. So you have layers of different materials. This is an example from Bedford et al. In 2022, which is now. So they were doing experiment by producing these samples made of different layers, and they observed how the strength was reducing and also how the stability was changing because of this layering. Also, there is the concept introduced by Rice in 2009. They can be strong, but can become dynamically weak because of the way you load the fault. Again, this is from previous literature. There are different materials here, but you can see some similar behavior. The material here are essentially clays with different content of quartz, different content of illite, smectite, but the message is the same. Here you have the velocity, you have the friction coefficient, you have room humidity and wet experiments. And for example, take this figure here, you can see that these room humidity clays can be quite strong. They become even stronger, 0.8 at velocity of centimeter per second, and then they become dynamically weak when the velocity are at 1 meter per second. This was the case of the Wyont disaster in 1963. But this is the case from the JFAST, which is quite similar. So the behavior is the same, the strength is a little bit lower. And this is an example from Aretusini with the analogs material, so made of different components of clay and quartz. And the concept is always the same. So the material can be strong, but it becomes weak with the velocity. But already in 2002, there was this concept that some sediments, clay-rich sediments, can be velocity strengthening in general, but sometimes allow earthquakes and becomes velocity weakening with an overall neutral frictional stability. This was Bilek and Lake in 2002, so there was this idea already. In 1988, there was this idea already because this was the paper by Scholz suggesting that the stability can be different. So something that was conditionally stable can be unstable if under dynamic loading condition is subject to a velocity jump exceeding delta V.
Elena,
sì.
Sorry, if you are using a cursor, we don't see the cursor.
Ah, okay, because it's here in the other screen.
Yeah, exactly.
Right.
So you need to put a pointer or something red.
Okay, thank you.
If you are not using, forget me.
Yes, it can be useful. Thank you very much. In fact, here I'm reading here. It can be stable under quasi-static loading, but can become unstable under dynamic loading, is subjected to a velocity jump exceeding a certain delta V. And there is also the effect of loading rate of static friction and the rate of fault healing during the earthquake cycles. So during the earthquake cycles, because of healing, also the strength can change. So this is an idea that was already present also in 1998 and before. This is some recent literature. One is the paper by Faulkner immediately after Tohoku, so 2011. This group of people in the running experiment derived the concept of frictional properties of clay-rich material vary as a function of slip velocity. Then also in our laboratory, we derived some similar conclusion that KC and DC, which determine the stability criterion, are not constant but evolve with the velocity. There is Lehman in 2011 saying that the rheological critical stiffness or the loading system stiffness must vary systematically as a function of loading velocity. So there is again this concept that all these parameters, which for us are important to determine if the mechanical behavior will be stable or not, and if the energy release will be high or low, they vary. So experiments, we were in fact talking quite a lot of experiments, but how we perform the experiments in general. First of all, when we run experiments, we need samples. So if we don't have samples, we at least can produce analogs materials, so we need the mineralogy. Unfortunately, this is the situation actually of the IODP scientific drilling programs. And there is also some more from the ICDP scientific drilling programs. So we have the log files and we have the cores of quite a large number of places around the world. The machines are huge. We have quite a lot of machines and they are very different. I just recall 4 machines here because of a recent paper published, for example, Hikari 2020 for the Igurangi, Kenningsberg 2020 for Sumatra, Carpenter for Safod, Aretusini for the Igurangi. And these machines are of this kind. So we have a single direct shear, we have a biaxial deformation apparatus, we have a triaxial deformation apparatus, and a rotary shear apparatus. Why we use so many machines? Generally, because all these machines are able to illuminate aspect of the spectrum of slip behavior. And so in a sense, they are complementary. For example, this one, which is the single direct shear at Marum, can run experiments approaching the condition of the convergent rate, so millimeters per year. One of the limitations is the displacement, because it's limited, also because for running experiment at such rate, you should wait for years, in fact. So it's millimeter of slip. On the other side of the spectrum, there is this kind of machine, which is the rotary shear machine, which runs at 1 meter per second for meters. And so we have the chance of using a vast range of conditions. And I will focus for the rest of the talk on this machine, which is called Shiva, and is a rotary shear apparatus, in fact. I promised to talk of some limitations. In fact, one of the limitations is for sure the applied condition, because we are not able, for example, to apply temperature. Not all the machine can apply temperature, which is quite important. Some machines, it's limited in the normal load that we can apply and the effective normal load we can apply. So we cannot simulate the real depths of subduction earthquakes. One of the limitations, for example, in the machines like Shiva, which is a rotary shear, is the type of samples that we have. This is the cores, the type of material that we investigate. They are not cohesive, so they are gouges. Essentially, they present like this, and they must be confined. Confining these gouge with fluid is challenging for this kind of machine. Here we have some result from Kuo in 2021. This is a sample assembly that he built, design in Taiwan to confine the gouge and to pressurize also the fluid. This is a solution that Stefano Rettusini found to confine the gouge and the fluid. So only now we are in the condition of studying, for example, thermal pressurization in gouges. The thing that we generally do in this kind of machine is to take the gouge in sample holder like this one, sorry, and to put some drops of water on the sample to have partially saturated condition in the end. And this is the kind of experiment that I will show later. This is a very nice compilation of data that I found from Saylor in 2020. Why I'm showing this? Because it's nice to see how different machines can work together. This is a parameter which is somehow a false friend. In fact, is the seismological fracture energy compared to the experimental fracture energy. I think that we will have a dedicated talk next month on fracture energy, so I will not spend much discussion on this at the moment, but apparently this is the only or one of the parameters that we can compare from the experiment and the seismological estimation. And all the machine that we use on dry gouges, wet gouges, intact rocks, and the seismological estimation for megatrust earthquakes seems to suggest that there is some comparison. So they are comparable. And this is nice because that means that the experiments can represent what is happening in the megatrust regions. And this is just an advertisement that this is exactly what we want to do in FEAR. So we want to understand a little bit better what kind of parameters can we compare in between the different machines, and also what can we compare with the real earthquakes. So in the very end, this is a new compilation of data I would like to present, which is based in fact on the idea that we try to investigate the frictional properties of these sediments, and a lot of things are still unknown. I take the case of Sumatra Andaman because this is the situation for the 2004 earthquake. This is the slip distribution. Again, the models suggest that there was a significant slip and moment release near the trench. Is a region which hosted historically quite a lot of events in the past, which are very large. There was an expedition, the IODP expedition number 362, which took essentially the sediment, the input sediments to the trench, and produces logs and seismics. During the campaign, the seismics were not able to investigate the entire sediment length up to the trench. Here we have about 4 kilometers of sediments, and it was impossible to see exactly the structure of these sediments. So we know the type of units that were investigated here. So it's possible to recognize a 3 kilometer thick of sediments of trench wedge, one other unit which is called the Bengal Nicobar fan sediments of 1 kilometer thick, and the pre-fan pelagic sediments which is from 0.4 to 1 kilometer thick. So there is this distribution, but there are a lot of unknowns. The expedition was not able to drill exactly on top of the trench. So it was, they drilled 200 kilometers from the trench. So here, and here is the trench. And they recovered more than 1.5 kilometers of sediments. And the question is again, large raptors might not be inhibited if they nucleate down deep and propagate upwards through the upper region of the accretionary wedge, isn't it? What are the lithologies that favor this behavior, and where is the découpement? Because we don't know. And because we drilled quite far from the trench, we have also to make a sort of, to imagine, we want to imagine what is going to happen in there when the sediments enter the subduction zone. So because of this, we want to present two kinds of experiments. One simulates the velocity perturbation which are due to the rupture propagating up deep. So for example, the rupture is nucleating somewhere here and is propagating up deep and through the sediments. Another idea is to try to simulate a slow tectonic loading and the effect of a slow tectonic loading. So what we want to do here is to apply traditional slip velocity functions, or something that we call unconventional creep test. That means that we control the shear stress and we increase the shear stress stepwise regularly. So the machine is Shiva, and here I'm going to present some technical details. So Shiva is composed essentially of three parts. This is the rotary part that applies the rotation. This is the stationary part that applies the normal load. This is the place where we put the gouge, the sample. So the sample is in frictional contact inside here, and and here you can see all the devices that we use to measure our variables. The important one in this case are the shear stress and the velocity, which are exerted and controlled here at the motor. The velocity is measured here, and the shear stress is measured here. So the fault is here. We measured the velocity before the fault and the shear stress after the fault. Some other technical details. Generally, we also apply a pre-shear or running the samples at 10 micrometer per second. This is because we want to reach a sort of similar condition, similar initial condition for all the experiments we run, and also because we want to organize a little bit the gouge before running the experiments. This is a classical velocity control test, which consists in applying this velocity ramp and measure the shear stress, which is here in black. Typically, we start from 0, we go up to a peak value by elastically loading all the machine plus the sample, and then we record the weakening at high velocity. Here it's 1 meter per second. In the case of the creep and conventional creep test, again, we have this pre-shear at 10 micrometer per second to prepare the sample. And then we start, in this case, to increase the shear stress stepwise. In that case, the velocity is spontaneous. So all the events that we record is spontaneous. So you can see that also the acceleration is spontaneous and is different from the imposed one. And we have, for safety reason, to make an upper cap. So we have to stop to make a limitation to the velocity. The limitation is 1 meter per second here. So up to here, everything we record in terms of displacement and velocity is spontaneous. Our samples, in fact, are this one. So the sample core from the deep drilling projects, which is essentially this gouge, clay gouge. This is the sample holder, which is 55 millimeter in diameter. This is the distribution of our sample, the gouge inside the sample holder. This is how it is after the experiment. We ran 86 experiments on 7 different lithologies. We applied 5 MPa and 15 MPa. We ran experiment under room humidity condition and also water damped condition. We applied the pure shear stress, and we also ran the creep test and velocity test. The type of materials we have. So the site, the drilling site was here essentially. So we have all the column up from here to here. We selected some representative samples from this column here. So we selected these 7 samples, and you can see that they are mainly composed of calcareous soils and silty clay, plus this 61R, which is made of tufaceous clays, which is also important because Hooper's et al. Did some more specific experiment on this type of material for several reasons. When we do velocity test, what we want to measure is essentially the friction coefficient during high velocity, the slip it takes for the shear stress to drop, the peak in friction, and the dynamic friction, the one that we call steady state friction. Then we are also interested to see how this distance to achieve the stress drop is depending on the normal stress. And one of the reasons is because we can't apply large normal stress because of the technical limitations of our machines. You can see here that the gouges of clays are here, this group of experiments here, that the DTH, which is the distance to have the 95% of drop, more or less, is already dropped at less than 5 MPa of normal stress. That means that we do not expect a giant change if we, for example, run experiments at larger normal loads. And this is the type of unconventional creep test. In the unconventional creep test, as told, we have an imposed shear stress from the motor. Then we have a recorded shear stress from the load cell, which is on the opposite side of the machine. In red, you can see the velocity, which is recorded in that case and is spontaneous up to 1 meter per second. This is a zoom of this region where you see that finally, because we reach a peak in shear stress, it's not possible to keep the shear stress constant anymore, and we record a drop in shear stress. Menandrin, you have a question.
A potentially stupid one. I don't understand, how do you directly control shear stress, or do you control it through normal stress?
Okay, so the normal stress, it's easier. It's applied here by a piston. This is an electromechanical piston and is controlled here at 5 MPa on 15 MPa, and it's constant during the test. It's kept constant in feedback. The large motor here applies a torque. So essentially it's the engine that controls the torque supply. So the engine knows that I want to apply this kind of torque, and the motor is trying to keep this torque constant. The torque on the surface becomes the shear stress essentially. So here I'm controlling the shear stress, and here I'm recording the shear stress. And in fact, this is important because this is not in feedback. So there is not a control on the shear stress here. I just tell the motor that I want that torque. That means that if the torque, if it's not possible to keep the torque because the gouge is deforming and the friction is lowering, the motor will try to apply the torque, so increasing the velocity until it finally gets to its final value. So if the friction rises again, then you can keep the torque. Otherwise, the torque is going to decrease, because the friction resistance is decreasing, and this is very important to underline. Thanks.
Thank you.
Okay, now here. So if you zoom in this region here, that is the difficult part, because during the loading stage, the imposed and the shear stress are quite the same, are similar. But at a certain point, because the resistance, the frictional strength is lowering, it's not possible for the engine to keep the shear stress constant, and the shear stress is dropping. It's dropping because the engine tries to follow and to increase the torque, trying to restore the shear stress that it wants to apply, but it can't because the frictional strength is reducing. So that's why we have the acceleration. This is the acceleration in red, and this is the slip accumulated meanwhile. We can measure quite a lot of parameters thanks to this kind of experiment, because we can measure the initial shear stress, we can measure the peak in shear stress, we can measure the dynamic shear stress, but also the TH, which is the time it takes to go from an initial velocity to the final velocity. And then we can define also parameters related to sleep. So for example, the sleep, which is required to accumulate before this event, and the sub-C, which is the classical sleep weakening distance. And here is another type of experiment. So you see here that the lithology was to facious clays. This is not a different kind of experiment, sorry. This is a different kind of lithology, because now we are running experiment on silty clays. And the picture is a little bit different, because as you might see, even here, when we try to apply them to keep the shear stress constant, it was not possible anymore. So it was possible, but the frictional response was quite pretty unstable. So we recorded these oscillations. In the end, the fault material was able to recover the stress. So the frictional strength was again constant, re-strengthen up to this point here, when finally it started to drop again.
Elena?
Yes.
Sorry, it's Chris. Just a quick question. The plot on the right, the units of time are seconds, but then it says 10 to the 6.
Milliseconds, sorry.
This is milliseconds. Okay, yeah, because,
yes.
And on the left, also milliseconds? No.
It's always milliseconds, because it's 10 to the 6. So
Okay.
it's milliseconds. This event here lasts a few seconds.
Okay, thank you.
These last minutes, like 1 hour or 2, depending on the loading rate. So this is say minutes, and this is seconds. Okay, another important difference is the acceleration, because again, the acceleration seems slower, it takes more time. The delta sub-zero is larger, because it's 20 centimeter, and this is the sleep required to achieve this kind of event, the dynamic event, let's call it like this. And again, we can measure all these parameters. Another important aspect to underline and to show is that if we have a group, at least the 3 lithologies, so silty clays, tufaceous clays, calcareous gouges, we can see some very important difference in terms of shear stress versus sleep. So before that, we were seeing the time, the dependency with time. Now we are seeing the behavior with sleep versus sleep. And you can see that here in dashed line, you have these sleep events. These sleep events here are of the order of 20 centimeter per second, 10 centimeter per second. This is the shear stress here. And you can see that we have oscillations in shear stress. I use this red triangle to remark the moment in terms of sleep, where we start to see the acceleration toward the final event, the dynamic event. So it's happening at 20 centimeter, 30 centimeter. But if you see the tufaceous clays, the behavior is completely different, because in less than millimeters of cumulated sleep, you can see the onset of this acceleration toward the dynamic event, which is of this kind. It's this one. And also the same behavior is recorded for calcareous gouges. So the behavior with sleep is completely different. And now we can try to make all the observations together. I know that this is a little bit busy, this picture, but I think that there are important information to show. So in red, we have the result from the velocity test. In gray and in green, we have the result from the creep test under room humidity condition. And in cyan and in blue, we have the result of the creep test under water condition. So we put all together the result of this experiment. The difference, for example, the difference from the gray and the green is the fact that we apply the pre-shear stress to have some pre-compaction, and we decided also to not apply the pre-shear with the pre-compaction, because we wanted to see the difference. And so we have all these results together. This is the initial shear stress. which is quite high in all the conditions except for the water. This is 3 MPa. These were results run for a normal stress of 5 MPa. That means 0.6 more or less of friction. So that means that the strength of this material was quite large, quite high. The peak in shear stress as well was high. In terms of wet experiment, the strength increases. For example, in case of the tufaceous clays, these are the tufaceous clays, and these are more or less the silty clays. And you can see also that the D sub C, so the slip weakening distance, is decreasing. Decreasing with what? We decided to introduce a variable which is called the apparent stiffness. The apparent stiffness is calculated from the last shear stress, so the zero shear stress that we measured here, this one, to the D sub 0, sorry, this is 0. So the slip which is required before having the dynamic event. And we see that dependent that if this apparent rigidity is increasing, we have that the DC is decreasing as well. Other parameter that we can measure is the TH, for example, and the stress drop. So this is a percentage respect to the tau peak. And the stress drop is of the 20%, for example, for silty clay, but it's quite high, for example, for the tufaceous clays. It's definitely higher if we have wet, in the case of wet experiments. The TH, that means in a sense the acceleration, is obviously constant for the velocity experiments, but it's quite variable for all the other lithologies. It's impressive that for this material here, which is the tufaceous clays, this is pretty small. So that means that the acceleration is very, very fast. Instead, in that case, for example, this is a case for the silty clays, is quite large. Another thing we can measure to have an idea on how much energy we have to propagate instabilities is the driving energy. So if we take the balance here of the energy, we can define the breakdown work as the area integrated over slip here. And in the classical seismological interpretation, the triangle here is the total energy, and the energy in excess is going to be this triangle here. We can measure both at this point because we have all the ingredients that we need. We can measure the breakdown work, which is, I would say, similar for all the lithologies. But if we look at the driving energy is different. This is because the initial strength and the initial peak are a little bit different, and that makes quite a large difference. So just to summarize all these new results, we have identified that we have at least 3 different grouping lithologies: the tufaceous clays, the carbonates, and the clay-rich samples, silty clays. These red samples, to summarize, are strong, are capable of accumulating larger elastic strain energy, and the energy is released quite fast because the D sub C is very small. This makes them likely the preferred sites for seismic slip. They are prone to accumulate elastic strain required to produce a locked patch on the plate interface, even at shallow depths. The question is, maybe they host rupture propagation. Then we have black samples, carbonates, which are very similar to the red samples, except that they have a strength which is a little bit larger, higher, but they are less efficient in releasing the stress. And then we have the clay-rich, the silty clay-rich samples, which are strong, but definitely dynamically weak. They have a strong dependency on velocity. This is something that we haven't seen in these results. They exhibit a wide range of slip behaviors, all these slip events that you have seen in a previous slide. They release the stress slowly. The D sub C is very large by creeping, but also through small and fast events. They are less efficient in preserving the energy of seismic instability, but can slip very easily. And then in the case of water, it's also interesting because the wet material that are representative of the shallowest portion of the prism cancel the majority of the observed slip behaviors. So all these slip events disappear. And tufaceous clays and carbonates are strong even when wet. They stay strong. The stress drop are larger in the case of wet sediments under room humidity condition, but the D-sub-C for the wet experiment is quite similar. And also, if we come back to this slide, for example, this one, we can see that in the case of the peak and in the initial shear stress, in a sense, the results are quite comparable if we load gradually with this grip test in here, or if we load with a velocity pulse. There are differences which are interesting and need some more investigation. Similar results were also previously found in Costa Rica. So we tested similar materials, wet silty clays and wet oozes, and the results was very similar. So in wet silty clays, when sheared very slowly, they have a low shear stress, can store little elastic strain energy. During rupture propagation, the strength stress is small, and also the stress drop, but the rupture will easily propagate because of the very low fracture energy. And for the wet woods, our results, our conclusion was that the wet woods can probably store more elastic strain energy, so they can store energy even when they are considered weak. So this is just some discussion that we are trying. What we want to summarize all the results that we had from this novel experiment. So if this is a sketch of the subduction zone, the idea is that in this very shallow region where we can simulate the condition of the shallow subduction earthquakes, we can imagine that this region here is made of a volume of sediments which are very thick in some cases. Each of these sediments is behaving differently. So one first hypothesis can be that, for example, in the shallowest part, we will have these wet clays that can propagate fast slip events, small but fast slip events with releasing low energy. Then underneath, we have short living slip events that produce these accelerating creep events. On the bottom part, we have this material which is really strong and can produce high energy and release the energy in fast slip events. So the final behavior of these thick sediments is going to be regulated by the interplay between these lithologies. A different hypothesis is, for example, that the energy produced here is all released in this layer, which is the deepest one, and then is somehow stopped because the energy is used to produce these short-lived events, and it never reached the upper layer where it could propagate for larger slip. The other hypothesis, the other idea is that once the sediments enter inside the subduction zone, the situation is a little bit different because of the compaction is expected to be compacted underneath the arc. And we expect some high energy fast slip events, very small short living slip events at the contact between the upper part where we have all the material accreted and the lower part, which is compacted at this point and dehydrated. And we could have some low energy fast slipping events even in this place, but also in the upper part of the megatrust. So I'm here arrived at my conclusive remarks, which are quite simple with respect to the complexity of this novel experiment, that the frictional properties of sediments at the subduction margins are variable. This variability affects the slip behavior of all materials, which are sediments. In this case, the slip behavior depends on the lithologies and also on the loading history. All materials can be strong and can accumulate elastic energy. All materials can be dynamically weak and release the stored energy in a variety of slip behaviors, and the fault zone is a volume. We should consider that the fault zone is always a volume containing different fault materials, and the overall behavior of the fault derives from a combination of all these mechanical properties with the surrounding. So this is my conclusive remarks. I leave you with this slide.
Thank you, Elena. Thank you very much. I invite everyone to unmute your microphone and to thank Elena for the presentation.
Very nice.
Very interesting.